Hey class, and welcome to a video for I wanted to make a video for the last Wiley Plus homework problem. In this problem, we have a situation where you have a car that's driving on a little bit confused, and that's okay. And engineers intentionally banked curves in order to make it so that cars could actually go around the curve with zero reliance on friction. And so, if you're relying with zero amount on friction, what that means is the only thing providing your centripetal force, again, keeping in mind that your needed centripetal force is in this direction. Your centripetal acceleration and centripetal force would have to be in towards the center of the circle. If you're not using friction at all, the only force remaining to provide that centripetal force is actually a component of your normal force. Because if we're driving around the circle with no friction, let's look at what a free body diagram would look like. We have our weight going straight down, and we have the normal force perpendicular to the road, and that's all. So if we make axes, now going with axes that are just horizontal and vertical as normal, what we can see is that the only thing pointing in the inward direction towards the center of the circle is a component of your normal force. You can use geometry to prove that the angle between the normal and the vertical y-axis is the same as the angle of the ramp. And so you should be able to look at doing some of the forces in the x direction are going to be equal to m times your centripetal acceleration, while some of the forces in the y direction equals 0. So the normal force times the cosine of the angle minus the weight will equal 0, and so you can actually observe that the normal force will equal the weight divided by the cosine of the angle. And a really cool thing happens from here. If we do the sum of the forces in the x, then all we have is the normal force times the sine of that same angle, the angle of the ramp, is equal to mv squared over r. And if we plug in the normal, we get mg sine theta divided by the cosine theta. Again, observing that this right here is our normal force, right? And that equals mv squared over r. And so you can actually solve for the angle of the ramp from this equation. Now that's when how the road is designed. As we're told here, this road is designed for a car moving at one exact speed of 56 kilometers an hour. All right? The moment the car starts driving at a speed less than that, in this case when it's rainy, they're driving at 37 kilometers an hour instead. If they're driving below that speed, the car is actually naturally going to want to drift down or slide down the ramp due to the weight force. So what your friction force then is going to be is a force that's parallel to the surface as always, but in this case it's going to be up the ramp because it's helping keep you from sliding down. So this is a trick. If you're driving around a banked curve, if you're exactly at the recommended speed, you need zero friction. If you're above the recommended speed, friction is going to keep you from flying off the track and point down the road. And if you're going below the recommended speed, your car would actually naturally start to drift down, and so friction would be pointing up the ramp. We'll unpack this a little bit more in class tomorrow too, I think, because it's such a fun and interesting example. But anyway, the first thing you have to do, again, as I mentioned, is use this equation here to solve for the angle. We can see our masses will cancel. Sine over cosine is tangent. And if we divide by the g, we could see that the tangent of the angle theta is just going to be equal to v squared over rg. So you can get your angle there using, again, the 56 kilometers an hour converted into meters per second. Now, for the second part of the question, now we have to look at a situation where we have friction. So now we have this new free body diagram over here where we now have friction as well. You can actually tackle this in one of two ways. You can either use the same x and y axes that I showed here with horizontal and vertical, or you can rotate your axes. Both ways are going to involve a fair bit of work in algebra. I'm just going to try to get you guys started. So if we're going to stick with the horizontal and vertical axes like I showed here, you're again going to have to do some of the forces in the x and in the y. So I'm going to move over here to make a little more space. So we still have some of the forces in the x direction, and they're still going to equal ma. I'm calling this direction in towards the circle the positive x and up the positive y, just so you know. That way my centripetal acceleration is positive. And then in the vertical direction, the sum of the forces in the y direction are 0 because it's not going to be flying up off the ramp or going down. You want to keep it at a nice stationary level in the vertical direction. So if we break down our forces now, we can observe here, it might be a little tricky to see, but your friction is going to have an x component and a y component, and your normal force is going to have a y component and an x component as well. So you have to add all of those up. So in the positive x direction, we will have the normal force that's in the x direction, so that's the normal times the sine of the angle. Again, that's the opposite side here, so it's normal times the sine. Then in the negative x direction, we have the x component of the friction, so that's the force of static friction, times the cosine of the angle, and that's all. So that equals mv squared over r, mass times centripetal acceleration. Then in the y direction, we have the y component of the normal up, so positive normal times the cosine of the angle theta, plus, because again, now our friction has a positive y component because it's going up the ramp, so we have the force of static friction times the sine of the angle theta, and then we have minus mg, trying to scoot us over here, minus mg, the weight, equals 0. And now we know, keep in mind, right, static force of friction, when we're looking at the minimum possible value, is going to be equal to the coefficient of static friction times the normal force. If we plug that in here, boom, and over here, boom, we now have two equations where the normal force and the coefficient are the only things we don't know. The algebra does get hairy. I'm going to tell you guys that right now. All right? But if you do your algebra well, you should be able to solve for the normal force in one equation and plug it into the other. For example, if we started with the y equation, we'd have normal cosine theta plus mu times the normal also times the sine of theta equals mg. Factoring out the normal force, you get the normal times cosine theta plus mu sine theta equals mg, and then you can divide by this entire term to find the normal force, and then plug that guy in to your x equation and try to solve. Keeping in mind here, all right, this v now is the v at which we need friction, so that's the slower velocity given in the problem statement. The theta, though, is the same theta. The theta of the ramp is fixed. You can't adjust that. All right? So I'm going to just stop there and let you guys try to complete the rest of the problem on your own. If you have additional questions, though, please don't hesitate to ask. And other than that, have yourselves a box-worthy evening.